Like I said, I think we were in chapter 7, and in chapter 7, we're really talking about types of reactions. And again, different ways to classify these reactions. As I think we talked about last time, there's really sort of two sort of big classifications of reactions. And underneath those sort of big classification of reactions are more specific ways you can sort of classify the same type of reaction. But ultimately, all reactions pretty much boil down to kind of three reasons why a reaction takes place. Um, One is the formation of a solid or a precipitate. One is the formation of water. And the third real reason pretty much a reaction takes place is there's some type of transfer of electrons. So again, all reactions pretty much will boil down to one of those three things basically occurring. Um, and those two big classification of reactions were double displacement reactions. And double displacement reactions have a general formula of AB plus CD. And how you recognize these things are they are two ionic compounds, which means you have a positive guy and a negative guy. And always when you have that situation of two ionic compounds coming together, pretty much the same thing always occurs is the positive guys will switch partners. So this guy will come over here, this guy will come over here, and they basically will form two new ionic compounds on the other side. And the result of sort of this type of reaction is this is pretty much the big classification of reactions that involve either a solid being formed or water being formed. So this basically this reaction takes care of kind of the formation of water or a solid basically be happening here. And obviously one of your products there would either be a solid or a or water would be formed. All other ones, again, are we'll talk about a little bit later on in this chapter here, which are redox reactions, and those involve the transfer of electrons. And a redox stands for oxidation reduction, which means actually both things are happening, and that involves basically electrons being transferred from one substance to the next. Now, in our talks earlier, I think we started with our double displacement reactions, and we talked about a more specific classification, which is a precipitation reaction. And again, the difference here is not much other than we essentially get some type of solid that is formed on our product side. We also talked about three types of equations that you could write a lot of times for double displacement reactions, but you can also write them for other reactions, including redox reactions. But in a lot of cases, double displacement reactions is where we see these type of equations. So if we had something like a little silver nitrate plus some sodium chloride, once again, that's a positive, negative. So they're going to switch partners here, like so. And when we do put it together on the other side, remember, we do want to just get the correct formula down first before you do anything in terms of balancing. And in this case, we will end up with silver and chloride coming together once again, two new ionic compounds. Now, one of the things we talked about was how do we know if we're going to get a solid or not when we put some, and those were was the very end last time. And for example, anything in group one is going to be soluble in everything. So when we get to something like sodium nitrate here, we know it's going to be soluble, which means it will get the aqueous symbol, which means it's basically a solution. So you have no solid basically in there. Now, things like chlorides, bromides, and iodides, they are soluble in everything. But if you remember, there were sort of three exceptions for those guys. And those three exceptions were something like silver, lead, and mercury. And because they are normally soluble in everything, and in this case, this is an exception, it will be the opposite, and it will actually be insoluble. And things that are insoluble based on solubility rules are the guys that get the solid and what would obviously make the precipitate in this case. So this equation, as we've seen before, is balanced. This is again what is obviously referred to as the molecular equation. Now we could take this equation and really describe sort of what is happening, say, in the beaker as you mix these two solutions together. And if we take that guy, thank you. And we really write an equation that describes sort of what's happening. Remember that these guys are really strong electrolytes, right? And strong electrolytes are things that when they are in solution will 100% break apart into ions. They will not stay together. So really in solution, we have something like silver ions floating around. And we got some nitrate ions floating around from our first guy here. We also have some sodium ions floating around and chloride ions floating around. On the other side here, we have some sodium ions floating around and some nitrates. And now anything that is a solid, a liquid, a gas, a weak electrolyte will usually be kept together in this type of equation. So here we would keep together the silver chloride. And this equation here is what is sometimes referred to as the total ionic equation, our complete ionic equation. And this is really describing what's happening when we dump these two solutions together, because both of these solutions are a strong electrolyte. When we do dump it together, basically in that solution, we basically have these ions floating around. Now, when we have this equation, we can look on both sides of the arrow and we can find ions that are exactly the same on both sides. And you should have the same amounts. So in this case, the nitrate on the left and the nitrate on the right, sodium on the right and sodium on the left. These are exactly the same on both sides. And these are what are referred to as spectator ions. And spectator ions are pretty much what it sounds like. They're pretty much still floating around the solution. So they're just hanging out, floating around the solution. They're really not part of any type of product being made in this particular reaction. So typically what we do with the spectator ions is we cancel them out on each side. And that's again why you should have equal amounts of those guys on each side. And that leaves us the third type of equation, which is really describing exactly sort of the reaction that is taking place when you throw those two solutions together. It is really the silver and the chloride coming to find each other and making, we'll call it a blue solid, but it's just a white solid actually, in this case, and make some silver chloride. And this is what is referred to as the net ionic equation. And again, as you can sort of see there in my picture, again, the sodium ions and nitrate ions, they're just continuously floating around. They're not forming anything here. And again, that is exactly what's happening here. And that's really the basis why this reaction is taking place, is for that formation of that solid, which again is one of those three reasons why a reaction takes place. Any questions on any of that stuff there? I think that's what we talked about, I hope. Yeah. All right. So let us continue on. So we're going to talk about acid and base reactions as well. And acid and base reactions also fall under the double displacement banner. So as we just saw with sort of our precipitation reactions, which by the way, the one we just did there is a precipitation reaction, that accounts for the solid being formed. And typically speaking, when we have an acid base reaction, it's going to account for water being formed basically. So this is really the one that is going to kind of form water when we do that. So let's talk a little bit about acids and bases. Acids have sour taste. They cause changes in litmus paper. So if you use litmus paper and you put an acidic solution on it, it basically will turn red, and that's how you know it's acidic. They will react with metals to perform hydrogen gas, which I think we've done in some experiments where you kind of put your thumb over and you did the popping sound and all that kind of stuff. It will also conduct electricity. There are strong acids, which are strong electrolytes, which will conduct electricity really well. There's also weak acids, which are weak electrolytes, would still be able to conduct electricity. Bases, on the other hand, have a bitter taste. They feel slippery. Most soaps, drain cleaners, those type of things are bases. They will actually turn litmus paper blue. So if you ever use litmus paper, and again, it kind of turns blue after you put your solution on it, that means that that's a basic solution. Just like acids, there are strong bases which conduct electricity really well because they completely break apart. And there are weak bases as well, which can conduct electricity in addition. So an acid is a substance that basically has the ability to produce H plus ions in solution. When we talk about acids, specifically, oftentimes H plus and H3O plus, which is the hydronium ion, are used interchangeably. So they sort of represent the acid part of the solution. Also, H plus is sometimes referred to proton, and that is because hydrogen has one proton and one electron and no neutrons. In order to become positively charged, you have to lose an electron, so it leaves it just a proton. So in acid-base chemistry, you'll sometimes see H plus, H3O plus sort of used interchangeable in so form. And that's really what makes something an acid, is that ability to plus ions floating around in that solution, freely floating, not attached to anything, just kind of freely floating around in that solution. It's really what makes it a sort of strong acid. Strong acids are strong electrolytes, which means, again, they will 100% break apart in solution. They will not stay together. There's sort of a list, and that's a partial list there, but let's kind of make the list here of strong acids. And strong acids are good ones to know because there's not too many of them per se, which means if you kind of know which ones are strong, by default, you'll kind of know probably which ones are weak because they're not one of the strong ones. So it's probably going to be a pretty safe bet. So this is going to be our hydrochloric acid, our nitric acid, also sulfuric acid, our perchloric acid, our hydrobromic acid, hydroiodic acid. So this list here of 6 acids, these are all strong acids. And as I mentioned before, it's probably a pretty good list to know as you go through chemistry. Again, because if it's not one of those, it's probably going to be a safe bet, like I said, that it will be probably a weak acid. So by process of elimination, you kind of know these 6. You kind of know the other ones are going to be more of a weak sort of acid. So what does that mean? It means really if you took hydrochloric acid, or you had hydrochloric acid in a beaker, it would 100% break apart into H plus and Cl minus. And that would be basically 100% of what you would have in that beaker floating around, is a bunch of H pluses and a bunch of Cl minuses. Now, in terms of it being an acid, it basically will be able to produce a lot of free H plus very quickly. It essentially just needs to go for a swim, and it's going to just drop in there a bunch of H pluses floating around. And that's why it's considered a strong acid, and will 100% break apart. In solution, you will have none of these guys still together. It completely breaks apart. None of the HCl units will still be there at all. Same thing with nitric acid. It will, again, 100% break apart into H plus and NO minus, NO3 minus there. Now that's different than, say, something like HF, which is a weak acid. And it will also break apart in solution. But it will mainly stay together. So if you were to look at a beaker of HF, you would mainly have HF guys floating around, and a little bit of H plus and F minus floating around in the solution. So since it's still able to kind of produce a little bit of that H plus in solution, it's still considered an acid, but it's a much weaker acid than something like HCl that's going to completely break apart and produce a lot of H plus really quickly. It will still also conduct electricity because there's a few bit of Again, nowhere near the amount of free H plus in that solution. Any questions on that there? Now, bases, on the other hand, a lot of strong bases contain hydroxide in the actual formula. And strong bases are strong electrolytes, which means that they will break apart 100%. And really, the definition of a base is the ability in solution to produce free hydroxide. So much like an acid producing that H plus, a base here's ability to produce free OH minus ions floating around in the solution is basically what makes that a base. Most strong bases come from group 1 and group 2 on the periodic table. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide. So if you go to group 1 on the periodic table and you go starting right at lithium and you got a little sodium, a little potassium, kind of come down and hang a right there to calcium, strontium, barium. All those guys there that have hydroxide in the formula are typically strong bases, which means, again, they will 100% break apart. So same idea here. If we did have something like the sodium hydroxide in solution, it's going to 100% break apart into these ions, which means you will have basically sodium ions floating around, a bunch of hydroxide ions floating around. And again, it's that ability to produce all that hydroxide really quickly is what makes it a strong base. Once again, you will have none of the sodium hydroxide units still together in solution. It will completely break apart. I would say probably the most common, and there definitely are others, but probably the most common weak base that you come across a lot is ammonia. And ammonia is a weak base. And basically, ammonia has to go find some water, basically. And what's going to happen is the ammonia is actually going to take an H plus from water. And the result of that is you'll make NH4 plus and a little bit of hydroxide here. So it's got to do a little bit of work, something like ammonia there, to produce some hydroxide. And they're still able to do so in solution, but it's, again, nowhere near going to be able to produce the amount of hydroxide that something like sodium hydroxide can produce, because sodium hydroxide, again, just needs to go in and is going to break apart and produce all that OH minus. Any questions on there? Now, when we have a reaction of a strong acid with a strong base, we typically get a couple of things that occur. So, for example, when we take a strong acid plus a strong base, we typically get two things formed. We get a salt and we get water that is formed. And water obviously is our H2O. And a salt is just an ionic compound. And when we take a reaction of a strong acid with a strong base, it is really a double displacement reaction. All acid-base reactions, for the most part, are double displacement reactions. So if you took something like HCl and you took some sodium hydroxide, again, that's a positive negative guy, positive negative guy. So it's a double displacement reaction happening here. Our positive guy is going to come over here to our negative, positive to our negative, and that's going to give us a sodium chloride and our formation of water in this case. And this would be our salt, which is our ionic compound that was formed over here. And obviously this is our water that was formed here. So this result of a strong acid and strong base, pretty much always when we have a strong acid, strong base, the way we get water is the H from the acid, the OH from the base. So that is essentially where the water comes from, always in a strong acid, strong base situation. And pretty much the salt comes from what's left over, those two guys basically coming together here. So that is essentially always pretty much how you do it. So you could literally, if you're not sure, just kind of put your hand over the H on the acid, the OH on the base, and what's left, just put it back together to get the salt part of it. and the other part will always basically be water in this case. So this is, as you can see there, a double displacement reaction. This is also classified as an acid-base reaction. And what happens when we take a strong acid and strong base, no matter what combination of strong acid or strong base that you put together, basically what is happening is the formation of water. Water is essentially what is happening in this reaction. So if we were to take our molecular equation here and break it up into our total ionic equation, we would have H plus and Cl minus from our acid. We would have sodium ions and hydroxide ions from our base. We would have sodium ions on the right-hand side and chloride ions from our salts. And water, which is a pure liquid, much like a solid, will be kept together in this particular case. And this would be our total ionic equation in this case. And once again, we could look at this and see our spectator ions in this case, which are our chloride, and our sodium, which is the same on both sides. Those are our spectator ions. Which means if we cancel those out on each side, we again get our net ionic equation, which again is essentially what is happening in this reaction, which is that H plus from our acid is going to go find the OH minus from our base, and they have a super strong attraction to each other, and that is going to make water, which is ultimately what is happening in this case, and that is our net ionic equation. You could combo together, like I said, any combination of a strong acid, strong base, and if you go through the total ionic equation and get yourself to the net ionic equation, that's always going to be the net ionic equation. You're always going to basically make water, which again, as I just mentioned, is by they're called sometimes neutralization reactions, because you're basically just making water. Question on that there. There you go. Guess I jumped a couple of slides there. Now, here's a couple other examples there. Again, we have our salts here, which is, in the case of the top one, our sodium chloride. In the case of the bottom one, there's our potassium nitrate. And again, even if we took this guy here and broke it apart, that is a strong acid, which means it will break apart into H plus and NO3 minus. KOH is a strong base, which will also break apart. We will have some water here, which will stay together, and we will have our potassium nitrate, which will also break apart. Once again here, nitrate and potassium are found on both sides. Those are our spectator ions, and as you can see, there's the same net ionic equation we saw in the previous one. Doesn't matter the combination that you got going on here. We're going to basically make water in this particular case. Any question on that there? I will say, as it says there, as I scribbled over it, for the most part, a lot of times based on solubility rules, the salts are typically going to be probably soluble, especially with your strong acids, strong bases. But it is possible they won't be, but I would say probably 9 times out of 10 or even more, they're probably just going to be a soluble sort of salt that's still floating around in that solution. Now, before we kind of look at the other ones, what would happen if we did have, say, a weak acid in a strong base? How would that sort of look? So if we took HF, which is a weak acid, and we reacted it with sodium hydroxide, which is a strong base. So that is a weak acid and a strong base. This, once again, is still a double displacement reaction. And once again, here we have our H and OH, which are going to come together to make water. And our salt's going to be our sodium ion and our fluoride ion coming together, which will make NaF, right? And that's going to be aqueous. So in this case, when we would go to our total ionic equation, because we know this is a weak acid, it means it's a weak electrolyte, which means we would not actually break it apart in this next equation. So we would actually just keep it together, and we would have HF, the sodium hydroxide, which is a strong base, would break apart. and our water would stay together since it's a liquid. And here the sodium fluoride would break apart as well since it's a strong electrolyte. Now, a little bit different here when we look at our total ionic equation is how many spectator ions do I have in this case? I actually only have the sodium, right? It's the only spectator ion that's actually there in this case. And that's because the acid in this case will actually stay together rather than fully break apart. And what we will end up with is just the sodium ion breaking apart. And we will end up with this as our net ionic equation, which looks a little bit different. And again, because we have that weak acid or weak electrolyte involved, we will end up with this equation here, actually. And so a little bit different of a net ionic equation because we do have that weak electrolyte involved. I would say we probably won't come across too much of that in here, but that again is sort of how you would handle something that's more of a weak electrolyte. Again, you would keep it together through that total ionic equation. It would probably result in just, as we see there, one spectator ion versus two, and you'll still have it together there in the net ionic equation at the end. Any questions on that? So that's the net ionic equation, total ionic equation, and molecular equation. Question on acids and base reactions. Yeah. It is. So that's kind of like what we talked about when we did naming and writing formulas. So it's always positive guy first, right, followed by negative. So that's always how you do those guys. It's ionic. And acids, which are, really a lot of them are covalently bonded, but they're kind of treated almost like ionic compounds. This is the same idea there. The H plus comes first, and then the next guy. Other questions? Yeah. All right. So we're now going to sort of transition and talk about really the other type of classification of reactions. And these are sometimes referred to as redox reactions. And just like double displacement reactions, where they kind of take care of water being formed and a solid being formed. And under double displacement reactions, you can more specifically classify a reaction as a precipitation reaction or an acid-base reaction. Redox is sort of the big specific ways of classifying place, which is some type of transfer of electrons. So redox means oxidation reduction, and there's several different definitions of oxidation and reduction. So we'll talk about a few of these here. Oxidation basically means that you lose electrons. Reduction basically means that you gain electrons. So sometimes people refer to it as Leo the lion goes grr, which is loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig type of deal. Oxidizing is losing, reducing is gaining. But for the most part, in general chemistry, sort of what we're talking about here and probably your next couple of classes, these are the definitions that you would sort of associate with oxidation reduction, which involve electrons. There's also definitions for oxidation reductions that involve gaining or losing oxygen or hydrogen, which is sometimes used in organic chemistry because it's much easier to follow hydrogen and oxygen sort of being gained and lost as they're sort of sharing electrons. So what happens when somebody loses electrons or gains electrons? There's sort of a really easy way to figure out what is being oxidized and what is being reduced. And you can use like a basic sort of number line to help you figure that out. And usually on a number line, there's a 0. And usually to the right, there's positive numbers and negative numbers headed there to the left of 0. Now, when we lose electrons, are we going to become more positive or negative? We're going to actually become more positive when we lose electrons, right? Because then we have more protons than electrons. So if you see that on the left-hand side of the arrow, whatever you're looking at, that element is going from a more negative situation to a more positive, what is really referred to as oxidation state, but we can kind of think of it like a charge, then that guy is going through oxidation. Now, if you look at something and it's kind of going more positive towards negative, that is what happens when somebody gains electrons, because now they have more electrons than they started with, and that thing will be going through reduction. The nice thing about oxidation reduction reactions is they always occur together. So if somebody gets oxidized, somebody else is getting reduced. And the nice thing about that is if you could just figure out one of them, the opposite thing's happening to the other thing. So it's all you have to do is kind of figure out what's going on with one of them, and you know what will happen sort of with the other. So for example, if I look at, say, zinc plus some HCl goes to ZnCl2 plus a little H2 action there. Now, when we look at what is really known as oxidation states, for example, the zinc here, which is by itself and it's solid, it is not attached to anything, it's not combined with anything, it will have a zero oxidation state, or you can think of it as like no charge. When we look at HCl, HCl is really hydrogens +1 and -1 there for Cl. Zinc here is +2, right? And Cl is -1. And over here, hydrogen by itself, that is naturally how it comes. It has really no charge. So if we wanted to sort of figure out what is going on here in terms of what is being oxidized and what is being reduced, we could follow what these, again, they're really known as oxidation states, are numbers. And they are slightly different than charges, but we'll kind of maybe call them charges for our purposes here. We could look at the zinc, for example, right? If we look at the zinc, and if we take our little number line in this case, the zinc is starting at 0, which is like right about there. And on the right-hand side, the zinc ends up at +2, which means it is moving in this direction, right? Becoming more positive. So in this case, the zinc is actually being oxidized. Yeah. Now, if we look at the hydrogen in this case on the left-hand side, it has an oxidation state of +1, right? Which is like right there on my number line. On the right-hand side, the hydrogen ended up at 0, which means it started at +1 and now is moving towards 0, right? Moving more in the negative direction, which means the hydrogen here is being reduced. How about the chlorine? What's happening with the chlorine? Anything? Nothing is happening with the chlorine, right? On the left-hand side, it's -1, right? And on the right-hand side, it is -1. There's actually nothing happening with the chlorine. You could actually, if you wanted to, write a total ionic equation for this. So if you took this, and I maybe erase something here. So if we take our equation there that I wrote, and I break it apart into sort of what is happening, the solid zinc is obviously going to stay together because it cannot break apart. But that hydrochloric acid is a strong electrolyte, like we talked about. It will break apart into 2 hydrogens and 2 chlorides. The zinc chloride will break apart, as it's a strong electrolyte, into that and a couple of chlorides. And our hydrogen, which is a gas, will stay together in this case. So it will actually stay together. It will not break apart. And this would be really the total ionic equation in this example here. Get rid of that there. Now, when we look at this, our spectator ion in this case is our chloride, as we just talked about below. Nothing's happening with it. It's just hanging out, floating around, having a good time. Not much is happening with it. We will cancel it out. And we could actually write a net ionic equation that really describes what is happening in this reaction, which is, in this particular case, it is the zinc, as we talked about, which is getting oxidized, which means it is going to lose electrons. It's going to send some electrons over to the hydrogen, which is positively charged and going to gain electrons and form basically our zinc plus when it loses 2 electrons. And our hydrogen, each hydrogen will form a H and come together and make basically H2. So that is the net ionic equation that's really happening here. And as you can see, really what's going on is a transfer of electrons from the zinc to the H plus that's floating around the solution. And what really happens in this situation, for example, is let's say we had a solution, and in this solution, you would have H plus and Cl minus, right? And you've done this, I think you threw the piece of zinc in, right? And you put your thumb over the test tube and all that kind of stuff. So let's just say I had a solid piece of zinc just kind of hanging out in that solution. What's going to happen is when the zinc loses electrons, it's going to actually go from solid and then go for a swim basically into the solution. And when those hydrogens gain those electrons, it's going to come out of the solution as bubbles as hydrogen gas is basically what happens in this case. So you're actually swapping places. This is why when you did that, if you remember your zinc piece of metal, I won't say fully disappeared because they used a giant piece of zinc if I remember, but you know, it got smaller and stuff like that. And ideally it would have completely disappeared. And really what's happening is those zinc guys are going from the solid state into the aqueous state as ions. And that's again where you do find ions floating around in the solution. And if you had a little piece of zinc metal, it would completely go away. And all the zinc ions would now just be floating around the solution. And all the bubbles coming out are the hydrogen basically leaving the solution as a gas. Any questions on that? Yeah. Yeah, so for our class, it would be something that you'd be able to figure out like their charges, like if you just relax, like, you know, what's the charge of this guy in this compound and stuff like that. Yeah. So oxidation states are a little bit different than charges, and we're not going to go deeply into oxidation states. But for our purposes, just to help you sort of understand what's happening with the electrons, you basically would be able to figure out sort of the oxidation state based on the charge that you see there. And again, all you have to remember is anything that is by itself, not combined with anything else, anything from the periodic table by itself, along with things like H2O2, that's how they naturally come. They have really no charge or zero oxidation state, and everything else you'll be able to kind of figure out. Yeah. It's whichever one is actually losing electrons and becoming more positive as it goes from the left-hand side of the arrow to the right-hand side of the arrow. So if we look at the zinc on the left-hand side of the arrow, it's 0 basically. On the right-hand side of the arrow, it's basically a +2. So it's become more positive. And the only way it could become more positive is it has to lose electrons. And when it loses electrons, that means, again, it has more protons, which is why it's becoming more positive. So as I just mentioned, you could look at it like the charge on any ionic compound. You'll be able to kind of figure it out. In most cases, what we would see would be just like if you were asked, hey, what's the charge on calcium and calcium chloride? You should know it's +2, right? And things like that. So you could just use those type of things and be able to figure it out in that case. Yeah. Other questions? Really doing true oxidation states involving non-metals and non-metals, like we're not going to do too much in here at all. That's where you would have to kind of do some math and things like that. But for our purposes, really the ionic compounds, whatever their charges in their ionic compound would be their oxidation state. All right. So let's take a look at this here. If we're doing this reaction here, we're taking some sodium and reacted with some chlorine to make some sodium chloride. Again, if we look at what is happening here, that is just sodium by itself, which means really it has 0 oxidation state and no charge. That is chlorine, and that is, again, naturally how it comes. When the sodium, the chlorine come together, that is an ionic compound. So again, here we should know that sodium's group 1, which means it has a +1 charge. Chlorine is group 7, which means it has a -1 charge. And that's really, for our purposes, all you would need to know to figure out sort of what is happening in this case. And if we did our little number line in this case, we could look at our sodium, and our sodium on the left is starting at 0. And on the right-hand side, it is ending at +1, which means it is moving in this direction, becoming more positive, which means the sodium is going through oxidation. The chlorine on the left-hand side is starting at 0. On the right-hand side, ending at -1, which means it is becoming more negative, and it is going through reduction. So in this case, what is really happening is the sodium is sending over some electrons there. Again, a transfer of electrons is happening here from the sodium to the chlorine. And that is going to form our sodium chloride ionic compound in this case, right? I totally missed that electron. Let's take that go this way. By the way, when we have a metal and nonmetal together, which one always forms a positive charge? Which one's always positive, the metal or the nonmetal? Metal. So which one should always be oxidized when you have a metal and nonmetal together? The metal should always be the one being oxidized. The nonmetal always forms a negative charge in an ionic compound, which means the nonmetal should always be the one being reduced in this case. So it's really easy when you have a metal and nonmetal together because it should always happen that way. The metal should always be the one losing electrons, which is why they become positively charged, and should be the ones being oxidized. And the nonmetal should always be the one gaining it. Now, where the number line could help you is maybe you got metal on both sides, right? Or maybe you got looking at a metal. So for example, if I had, let's say on one side of the arrow, I had Fe with a 3+ charge goes to iron with a 2+ charge. Is my iron in this case being oxidized or reduced? Oh. So let's take a look and see. So on the left-hand side, it is starting at +3, which would be here, right? And on the left-hand side, I get my right and left together. My right-hand side there is becoming +2, which means it's actually moving in this direction. So you are correct. It is actually being reduced in this case. So even if you have sort of the same guy and they're all metals involved, you still use that number line to figure out what is being oxidized and what is being reduced in this particular case. So this type of reaction, as I mentioned before, is called a redox reaction. We will see a more specific classification of this type of reaction in just a second as well. Here's another example. Once again, that's magnesium by itself, no charge. Oxygen by itself, no charge. When they come together, that is when they gain charges. So our magnesium here is +2, our oxygen is -2. So once again, if you're not sure, you could look at the magnesium starting at 0, ending at +2, which means it is being oxidized. It is becoming more positive. And our oxygen is starting at 0 and ending at -2. It is becoming reduced in this case, right? And again, that is what we would expect here. He's sending electrons over, oxidized, and this guy is being reduced. So this is another sort of redox reaction, which, as we will shortly see, can also be classified a few different ways as well. Now, you can break apart this reaction here once again and sort of show what is happening in each of them. And these are what are sometimes referred to as half reactions. And they basically describe what is losing electrons, what is gaining electrons. This is what is referred to as the oxidation half reaction. And it's basically losing electrons. And the important part here, as we might have talked about previously, we see electrons written on the right-hand side of the arrow. And typically when you see that, that means somebody is losing electrons like they're being given off. So typically electrons will be on the right-hand side of the arrow. And here our oxygen, as we talked about, are gaining electrons. So this is what is sometimes referred to as the reduction half reaction. And in this case, the electrons are actually on the product side, which means that they're actually being gained and by the oxygen. They are called half reactions because when you add them back together, the electrons completely cancel out and you get the overall reaction that's happening here. Sort of like breaking that reaction into its two parts, its oxidation part and its reduction part in this particular case. The reason there are 4 electrons is each magnesium will lose 2 electrons each, right? For a total of 4 electrons, since there's 2 of them. And each oxygen will gain 2 electrons each. And that's how they each become O2 minus, right? Because there's two oxygens and they come apart and they each gain 2 electrons and now are O2 minus floating around. Any questions on that there? That I think is what we did when we did the burning of the magnesium, I think. Yeah. All right. All right, so as I mentioned, we're not going to really deal too much with the other definitions of oxidation and reduction, but just so, again, you kind of know, you could look at oxidation, and again, you probably won't see too much of this until you get to organic, but oxidation could also mean that somebody gained oxygen from reactants to products. So as you go from reactants to products, somebody gains some more oxygen than they started with. And the other one is they could lose hydrogen as they go from reactants to products. So that is 2 other definitions of oxidation. Along with reduction is that it loses oxygen as it goes from reactants to products and gains hydrogen as it goes from reactants to products. So again, we probably won't see too much of it, but if we look at this particular example here, we can look at the sulfur, and the sulfur in this case has gained some oxygens as it went from left to right, which means the sulfur in this case is going to be oxidized, while our oxygen here pretty much goes away. So it kind of lost oxygen in that sense, and it would be reduced in this case. And so this guy would be reduced. This guy would be oxidized, and it's really the sulfur in this case that's being oxidized as you go through it. Now, this would be a case where if you were really doing oxidation states, you would have to do some math to figure it out, but we're not going to see too much of this at all. But this is, again, just another definition. So now that we have sort of an overview of redox reactions, which once again, as I mentioned, are the big classification of a certain types of reactions, let's now talk about more specific ways to classify these reactions. And again, as we've been talking about, they do involve these 3 things sort of happening. The first one is obviously, as we've talked about, a precipitation reaction, which again is a double displacement reaction. And once again, positive, negative, positive, negative, positive guys switching partners. And right here is our precipitate, right, being made, and our solid being made here. So if you went through your net ionic equation, your total ionic equation to your net ionic equation, what you would end up with in this case is when you mix those 2 solutions, the barium ion from the barium nitrate will go find the chromate ion from the potassium chromate. And it is those 2 guys that will come together to make this solid. And again, really the reason why that would happen. So again, if you went through those kind of total ionic equation and canceled out your spectator ions, that is essentially what's going to happen when you put those 2 solutions together. It is those ions floating around. It is the potassium, the nitrate, which are spectator ions still floating around in the solution, not doing anything in this particular case. And as I mentioned, this is a double displacement reaction, or some people do call it a double exchange. And that is clearly how you recognize it. 2 ionic compounds. There's no other reaction that basically has 2 ionic compounds. Yeah. Yeah. It wouldn't, because you got to remember, and it's a good question, and it's really important, especially with these type of equations and stuff like that. For example, if you were given just the front part here, and you were given like, hey, what do you get on the other side type of thing. So remember that when you're sort of predicting formulas on the other side, you want to always make sure that you get the correct formula first and then balance it. So really, when you're doing that, what you want to think about is what are the basic units of this guy? And the basic 2 ions of this guy is a potassium ion, which is really just K+, even though there's 2, right? And the basic ion of the chromate is this guy. And those are really the 2 basic ions of that one guy right there. And really the two basic ions of this guy is barium with a +2 charge, and that is nitrate, which is one of those polyatomic ions. So that's the two ions that are here. So when they come together, remember, these are the ions that are basically floating around in the beaker, right? So these are the guys that are actually floating around. When they do come together, they're going to come together like we talked about with nomenclature to make an ionic compound. And they're only going to come together like they should, which in this case, we have a +1 and a -1, which means when you get to this side, you only need one of each, which gives you the proper formula. And when this guy comes together with this guy, that is a +2 and a -2, which means as they're floating around, they're just going to come together a 1-to-1 relationship here, which will give you this. It's at this point, now that you have the proper formulas, then you should balance it. And that's how the 2 gets to the front. And that's where it should be in that case. So it's a very common mistake. I think we talked about maybe when we're talking about writing equations and stuff like that, is people try to sort of put it together on the other side and balance it at the same time. And remember, you want to really just put it together with the proper formulas first and then go back and balance it. Because ultimately what's happening, as I mentioned, is those are really, if you just get it down to those 4 ions, those are really kind of the 4 ions that are just floating around, in that solution. So when they do find each other, they're going to come together in the correct ratio to make a proper ionic compound. Other questions? So here, as we saw earlier, is our acid-base neutralization reaction, but again, still a double displacement reaction, positive, negative. Once again, we're going to just swap these guys out. That's going to get our water and our salt, right? So again, also a double displacement here. Now here we have lithium plus fluorine, making lithium fluoride. This is now going to be a redox sort of category. And we see that with this being 0, that being 0, that being +1 and -1. In this case, what is being oxidized? It is the lithium, right? Because it's a metal, right? And the fluorine's a non-metal. And basically the lithium is going to send our electrons over, right? Because it's going again from 0 to +1, the lithium, right? Becoming more positive and being oxidized. And this guy is being reduced. Now, in addition to this being an oxidation reduction reaction and the one that we just saw here, this reaction here is a single replacement reaction. And a single replacement reaction is also a redox reaction. And it has this general formula of A plus BC. This is something that's either a metal and an ionic compound coming together. So this is different than a double displacement where you have 2 ionic compounds. Here you have just 1 ionic compound and a metal. The metal will come in and kick out the positive guy because a metal will make a positive charge. So it'll kick out the guy that has the same type of charge, and it will make a new ionic compound. And that guy that gets kicked out will come out with no charge on the back end. We actually saw these experiments when we did the halogens and the fume hood and the different layers. This is the single replacement reactions. In that case, we actually started with a non-metal and an ionic compound. And in this case, the non-metal will kick out the negative guy that is there. And it will form a new ionic compound, and that guy will come out with no charge. So a single replacement reaction will always look like this. This is, as the one I did earlier a second ago, is also a redox reaction happening. Again, 0 + 1, 0 + 2. Here, the zinc is being oxidized, going from 0 to +2, becoming more positive, and the hydrogen is gaining those electrons. So again, we have our electrons being transferred. So this is a redox reaction. This is probably more by people as a single replacement reaction. If you remember, in order for this reaction to take place, the guy coming in needs to be more or less reactive than what it's replacing. It needs to be more reactive. So for this reaction to take place, whatever is coming in needs to be more reactive than what is replacing. So A needs to be more reactive than what it is replacing. So if it's replacing the metal or the non-metal, it needs to be more reactive. If it is not, then the reaction will not take place. If you remember, when we look at the activity series for the halogens, activity increases which way? Which one's more reactive? Going up or down that group? Not everybody at once. Up, yeah. So reactivity increases as we go up, right? We saw the chlorine replaced the bromine replaced the iodine, but the iodine did not replace anybody when we did that, right? Reactivity. Now, in terms of metals, there is an activity series, and usually if you see an activity series, it's just a list of elements, and usually hydrogen is somewhere there. And when you would look at a list or an activity series of some other elements, anybody that is higher on the list will replace anybody lower on the list, and anybody lower on the list will not replace anybody higher on the list. So, for example, if you look at an activity series list, you would see zinc up here, and maybe copper over here. And what would happen is with the zinc reaction here, it will replace the hydrogen. But if you try to do this exact same reaction with the copper, which is lower on the list, it will actually not take place. So this reaction will not take place because copper is less reactive. So yeah, it's usually how they are. There's kind of a list of elements, and hydrogen is in the middle, and anybody higher will replace anybody lower, and anybody lower will not replace anybody higher in these type of reactions. So this is a single replacement reaction, which is a more specific of this redox reaction that's basically taking place. Involves usually a metal by itself or a non-metal by itself and an ionic compound. So that's again how you could kind of recognize it. A combustion reaction is another redox sort of reaction. And again, combustion usually falls under redox. This, I will say, is probably when somebody says a combustion reaction to you, probably the reaction that they are thinking of, which is sometimes referred to as an organic combustion. And that is because this is an organic compound. And an organic compound typically has carbon, hydrogen, and oxygen. And in a classic combustion reaction that's an organic one, O2 on the left-hand side, CO2 and water on the right-hand side is pretty much what you get. This is pretty much what happens when you light your Bunsen burner, right? You get the flame, a little bit of spark. Most of these guys are flammable, right? You get some fire. You do this with propane, butane. A lot of those guys, you'll get basically a fire that will occur. And that's what's on the bottom there, which is propane. So I would say probably 9 times out of 10, somebody's talking to you in your casual conversation about reactions, and you're talking about combustion reactions. I don't know why you're having that conversation, but they will probably be talking about this reaction. Now, really a more just general definition of a combustion reaction is pretty much this. You frankly only need O2. So any reaction that technically has O2 on the left-hand side there is a combustion reaction, or can be classified as a combustion reaction. But again, I would say most people are thinking of these type of combustion reactions where you have O2 and CO2 and water. But technically speaking, that's kind of all you need there. Some oxygen on the left, and it can be classified sort of as a combustion reaction. Any question on that? And again, this also falls under the redox umbrella of what's going on. Another type of reaction that also again falls under the redox umbrella are synthesis or combination reactions. I feel like that should be an N, maybe. And synthesis or combination reactions pretty much are what they sound like. You have two things make one thing. So they combo together, basically. So that is like the way you could recognize this as a synthesis or combination reaction. You see two things that make one thing, probably a safe bet. So here we have H2 and O2 making water. Two things make one thing, combination or synthesis reaction. Sodium and chlorine making sodium chloride. Two things make one thing, combination or synthesis reaction. Each of those can also still be classified as redox reactions. as hydrogen is 0 here, oxygen is 0. Hydrogen is +1 and oxygen is -1. So in this particular case, hydrogen is going from 0 to +1, becoming more positive, and it is actually being oxidized. Yeah. And this guy is being reduced. Again, if you number line it up, our hydrogen starting at 0, ending at +1. And our oxygen starting at 0, ending at -2, being reduced in that case. So these are redox reactions. These are synthesis and combination reactions. As you could see, you could classify the same reaction a couple of ways. Let's just take a look at this guy that we saw a second ago. This is a redox reaction, as we just talked about, right? Could this be classified as a synthesis reaction? Yeah, that's two things that make one thing. Also could be classified for the trifecta of, I see oxygen, which makes it a combustion reaction as well. Yeah, so this one reaction, depending on sort of what you're looking at, you could classify it as a redox reaction, a combustion reaction, or a synthesis reaction. I would say 9 times out of 10, probably people will classify this more as a synthesis reaction. Two things making one, but it technically can be classified as any of those 3 type of ways. So you definitely can classify the same reaction in a few different ways depending on what you're looking at it. Any question on that one there? The last type of sort of classification is really sort of the opposite, if you will, of a synthesis reaction. And this is a decomposition reaction, which essentially means we're going to break something apart. So in this case, we're going to start with one thing and make a couple of things. Yeah. So it's sort of the exact opposite of a synthesis. One thing makes a few things or 2 or more things. So here, if we run an electrical current across water, you will get hydrogen gas and oxygen gas that will come out of it. Again, one thing makes 2 things is a decomposition reaction. Once again, these are still redox reactions. If you follow sort of what's happening with the electrons, they are still doing that redox sort of classification as well. Question on that there. So to summarize here, to finish up this chapter, let us do this here. As we talked about in this chapter in terms of ways to classify reactions, really we have our 2 big categories, which are double displacement and redox. And under these categories, the more specific ways to classify reactions, the precipitation reactions, which is where we make a solid, right, is a more specific classification. Our acid-base reactions, which basically makes our water. And under our redox, which involves our transfer of electrons, we have our synthesis reaction. We have our decomposition reaction. We have our single replacement reaction. And we have our combustion reaction. So again, sort of big category up on top, more specific ways you could classify those reactions at the bottom. Again, basically here for synthesis, 2 things make one. One thing breaks apart into 2 or more things. Single replacement, one thing plus an ionic guy coming in. And combustion, some oxygen. And again, most of the time, CO2 and water involved. Obviously, our double displacement, regardless of which one it is, 2 ionic compounds where they switch partners and make 2 new ionic compounds on the back end here. Any questions on any of those things there? All right, we'll lay it up there for today.